Okay, are we ready?
Okay.
So yeah, today Ilker is going to continue second part on derived geometry. So please.
Yeah, thank you. So, let me first remind you what we did last time, very briefly. Last time, uh, actually, our purpose is to study, I don't know, different formulations or different descriptions, but equivalent descriptions of infinite categories. Okay. And last time we mentioned, I mean, today we keep discussing the same thing, but last time we learned, I don't know, several approaches. One of them is, so let's say, different description or different ways of specifying an infinite category of an infinity categories. Last time, so if you remember, we mentioned the notion of relative categories, right? So what was it? So it means that you just have a pair. So it's enough to specify this pair to describe an infinite category. So it's like, so this W is like a subcategory, uh, or sometimes we call weak equivalences. So for instance, it's the easiest way of specifying an infinite category. For instance, in the category of topological spaces, you can choose this W homotopy equivalences. Or in the category of chain complexes, you can choose this W, the category of morphisms of, let's say, quasi-isomorphisms. Okay? So it is one way of specifying an infinite category. Just consider this relative category setup. Or you can use, which is a particular relative category actually, model category structure. Model category structure. If you have a model category, then it is actually a particular relative category in which you also have additional information, cofibrations and fibrations. It's a nice computational tools, but for us, it is enough to specify this W, weak equivalences. And the second part, actually the essential approach we discussed last time, using topological categories. Okay? So using topological categories. And if you remember, so by using this, we we introduce infinite groupoid, right? Infinite groupoid of a topological space last time, which is like you have objects. Objects are your, topological spaces, and you have maps between topological spaces, and then homotopies between these maps and higher homotopies. So this is an important example, infinite groupoid, or sometimes it is called fundamental infinite groupoid. But this is nice because this leads to the definition of infinite zero categories. So therefore, if you want to study infinite zero categories, which means that you are studying infinite groupoid. But actually there is a useful fact, if you remember, any infinite zero category can be seen as a infinite groupoid of a certain topological space. So therefore this thing is like a spaces in the sense of homotopy theory. Okay, this is what we did last time. And also, by using this motivation, the next reasonable case, infinite one categories, or just infinity category, right? So it's like infinity category. So therefore, when we say infinity category, we mean infinity one categories, in which all higher morphisms are invertible, but you are allowing non-invertible morphisms only for when n equals 1 actually, right? And finally, we gave a formal definition. So this is kind of a category enriched over infinite groupoids, right? Which means if you consider the mapping spaces are actually infinite groupoids. Okay. So this is a topological perspective. So if you want to specify an infinite category, you can use topological categories actually. You can view these things like spaces in the sense of homotopy theory. Okay, this is what we more or less did last time. But now, today, we discuss infinite categories using simplicial sets. Okay, simplicial sets. Just let me get rid of this. Okay, so this is, of course, more combinatorial approach. So because simplicial sets are very useful objects, to understand the spaces like that. So therefore, we will use actually the same motivation. So if you want to specify an infinite category using simplicial sets, we have actually the following. The first motivation is the relation between, so let us briefly discuss simplicial sets versus a topological space. Okay, so this is the first motivation. So let me start with a notation. So this notation means for us, it's just geometric n simplex. Okay, so it's like components like this in Rn plus 1, such that, these are some standard terminology, right? So something like this. So this is what we call geometric n simplex or standard, the geometric or standard n. The components are positive. So this is actually the subset of Rn plus 1, this one. Okay, you're right. Maybe I should specify over here. Good. And you also have some maps, but pictures, So for instance, when n equals 0, you only have that just a point. When n equals 1, you have these things, right? Something like this. And when n equals 2, something like this, right? And it goes like that. And also you have usual maps, some maps with maps. So one of them is, let's call sigma I, which is a map like this, n plus 1 to n simplex, okay? Our degeneracy map. And so this is the ith degeneracy. And the other one, let me use delta I notation. It means this is just ith face map. Okay, this is n minus 1, and it maps to delta n. Okay, so this is the ith face map. Okay, so you just have, so it's like, I should use this. So it's like, so this is your delta 0. This is like delta 1. And this collapsing this h to a point, this is your sigma 0. Okay, so you have maps like that. Collapsing h and h. And you can have, of course, more maps when you increase n, right? So these are some standard notations. And now let us take a topological space. So given a topological space X. Okay. Now you can define a simplicial set. So define what we call this. Okay. So we are going to define this particular simplicial set. So like this. So it is like an assignment for any topological space. Okay. We assign this simplicial set where, of course, we need to specify each simplex. Okay, so its n simplices are just continuous maps. Okay, continuous maps like this. Okay, so therefore you have, very roughly speaking, you have your topological space. You are just looking at image of all of these things for instance, over here. Okay, maybe you have some pictures like this one. Okay. Good. So what is, so let's discuss some properties here. So for instance, this X actually, so remark. So this X actually can be determined by this simplicial set. Okay, this is the first property we should recall. So X actually determined by this thing X. Okay, this is the first thing we should recall. And the second thing, of course, by using these maps, we also have a diagram. Okay. So a diagram like this, so there exists, so for this simplicial set, there exists a diagram. Okay. So this is, so we have this, so let me just sketch. Okay, it goes like this, and the diagram is, here we have sigma 0, and delta 0, and delta 1. And likewise, you will have, okay, 3 maps like this. Maybe I should sketch these things like dashed arrows. Okay, this is a little, so notation is a little bit different because these are just images of these maps, okay, under this functor. Okay, actually, you have that functor. Yeah, it says contravariant. Okay, so therefore, these are just, so for instance, this one is just image of this delta I, which was a face map under this contravariant functor. Okay, so it's something like this. Okay, and it goes like this. So you have a huge diagram like this. And what is special about this diagram? Actually, we have a nice fact. So we actually have a junction between topological spaces by using this functor and simplicial sets. Okay? And we also have another map in this direction, geometric realization. So one direction is that one, and the other direction is something like this. And if so, given a simplicial set, by using actually these things, so we are going to actually discuss what is this delta n. So using these things, you can actually have the map in the reverse direction. So this is an adjunction, so what we call Coulomb equivalence. Okay, it means that if you look at the homotopy category of these things, they are the same. Okay, so therefore, if you want to study homotopy type of a topological space, you can study actually simplicial sets, right? So homotopy category, same thing, like this. Okay. Okay, so if you want to study topological spaces, up to V homotopy type, it's enough to study simplicial sets. So this is another important, I don't know, property, maybe, or fact. What else? So more notation. So let me remind you other possible notations which will be useful soon. So some notation. Okay. So first of all, this delta. So this is a very particular category of finite order sets. So this is this. So we denote by delta the category of finite ordered sets. So it means your objects are like this. You have order. Okay, so this is a typical object in that category, and the morphisms are non-decreasing maps. Okay, and the morphisms So in general, we use, this notation. I'm just reminding you. So you also have maps like this, which satisfies, this property. Okay, so non-decreasing maps. Good, and then now we have a definition of a simplicial set. Okay, so by simplicial set, we mean actually the following functor. A simplicial set, is a functor from this delta op to sets. Okay, and another notation. So in general, we just use this xn notation for the image, right? And also, since this is a functor from delta op, it's a contravariant, right? Okay, so we have morphisms like that. So these are just n simplices, the set of n simplices. This is just the set of n simplices. So this is our formal definition, this for simplicial sets. What else we should recall? For instance, there is a very special property for these maps. Okay, actually, these maps, such map, let's say F, induces a linear map. Okay, induces a linear map. Okay, so recall this terminology. So this induces a linear map. Okay. So F star, let's say something like this, from Rn plus 1 to Rn plus 1. Okay. And the definition of this map is given like this. So for each n, or maybe I should say, okay, ek, it maps to f, fek, which is efk. Okay, good. So for each basis vector, so it maps like this, and therefore, this map also induces a natural map on these geometric n simplices. What? Which one? One of them is n, right? N. Yeah, you're right. Okay, maybe I should. N plus 1 and n plus. Okay. The other way around. Okay, let me see which one. Okay, you're right. This is n, m. Good. And also there is such a map. Also there exists this map as well. Okay. The induced map like this. Okay. Also f star. But again, I guess same mistake. Okay. Okay. The problem is okay. I see. Because here I choose f the other way around. But okay. Sorry. You're right. Here, this f, we are taking f like this. But maybe I should be a little bit careful. Okay, in my notes, I choose the other way around, so this is the reason. So let's fix our notation. For such f, we have these induced maps. Okay, good. Okay. And also, let's focus on such f's one more time. Actually, these are always can be written in a special form. So by using certain maps, so let me write it down. So I don't know, fourth item, I guess. Such f, so every such f factors into a surjection followed by an injection. Okay, and if you have a surjection, you can always factor these surjections. Okay, you can write them as a sequence of what we call coface maps. Okay, so written as a sequence of coface maps, meaning it means maps like this. Okay, so I have, okay, careful. Okay, surjections. Sorry, we need to be a little bit careful. These are codegeneracy maps. Okay. Okay, so I try to be careful about my notation. So it's like n plus 1 to n. So it maps like this for each k. Either you map to k if k is less than equal to I, or k minus 1 otherwise. And for these injections, they can be written as a sequence of coface maps. Okay, so they are like delta i's. Okay, n minus 1, n, and it maps like this. So for each k, either you have k or k plus 1. Okay, something like this. So you can check. So one of them is like we are just collapsing one edge. The other one is like we are just embedding smaller simplex into a larger simplex. Okay, so you can check it carefully. So there is a diagram. So there exists a diagram like this. So this is your x0, x1, x2. So two maps in that direction, for instance. So delta 0, delta 1, and the sigma 0 here. And you can check three maps, delta 1, I don't know, delta 0, 1, 2, and the two maps, sigma maps, going in that direction. So you can fill the rest. Okay? So you always have such a diagram. And finally, the final, let's say the definition. Remember, we just discussed geometric n simplex. And also we have a combinatorial n simplex. So we can define, or just n simplex, combinatorial n simplex. So let's use this notation, just delta n. You know, this is a simplicial set, which is just maps, you know, in this category, delta category, into n. Okay. So if you go back and if you look at the other version with this, you know, topological version, you can easily see that the vertices, you know, corresponds to these maps. Okay? And the next definition, we will need what we call horn. Okay, horn of n simplex. So for such n, so we define the kth horn. Okay, something like this, and we use this notation. Okay, so to be something like this, but it will be very easy to understand when we sketch some pictures. So it is like, let me write the formal one. Okay. Okay, something like this, which essentially means you are just going to delete the interior and the face opposite to the kth vertex. Okay, so we will see, for instance, an example. For instance, you have this delta 1. Okay, let's say this is 0, 1. So if you want, let's say, this one, it means you are just going to delete everything inside and the vertex opposite to kth vertex, right? So therefore, the remaining picture is just something like this. So you are just deleting the rest, okay? Therefore, you end up with this. Or you can look at, I don't know, first horn. It turns out to be you are deleting this part, you are deleting everything here, and you only left with that point. Delta I of delta. Okay, let me check. Yeah. I guess I should, okay, delta n, right? Yeah. And for instance, let's look at this one. Okay, let's say these are 0, 1, 2. Let's say this is delta 2. Okay. And then, I don't know, so this one turns out to be, you are just going to delete everything, you know, inside and the edge, right? Or the face opposite to the zero vertex. So anyway, you end up with something like this, right? Or, so this is 0, 2, 1. Now this is, I guess, something like this. And finally, 2, 2. Okay? It's something like this. Okay? So these are your horns, actually, when n equals 2. And you can keep doing that. So this is what we call a kth horn. So let's see why this is important and what is the relation, you know, so how do we use these things to model an infinite category. Okay? Okay, maybe one final definition, and it will be clear. So what we call Kan complex. Okay. So definition. A Kan complex. Okay. So this is a simplicial set. Is a simplicial set. Let's say K, but for which we also have some extra condition. And this diagram is kind of fillable. Okay, let me just write it quickly. So let's say you have this diagram. Okay. You have this natural diagram like this. Your n simplex, your horn, and you have this map. And if this thing is fillable, which means that if there exists such map for any for any I, okay, but I is 0 between n. Okay, so this is what we call the Kan condition. So this extra condition is called Kan condition. Okay, so we will see why this is important. But first of all, an example. Example is, so remember the particular simplicial set we constructed. Actually, this thing, you know, sing x, right? This is actually a Kan complex. Okay? Is a Kan complex. I mean, why? I mean, because remember, so if you consider the geometric versions, right? This one is just a retraction. So there is a retraction, right? So okay, let me write it down. The horn, the ith horn, is a retract of the simplex this in the category of topological spaces. Okay, so you have a retraction. So therefore, this you can always have this diagram. Okay. So therefore, this map can always be extended to a map from the n simplex. So by using the retraction from n simplex to k horn. Okay. So this is an important property. So let's understand why this is important. Let's look at the following. Let's try to discuss everything, but now using more categorical language. Okay? So now let's discuss simplicial sets versus category theory. Okay, so this is kind of our second motivation. So the first motivation is, given a topological space, we just constructed a very particular simplicial set, which turns out to be a Kan complex. Okay, so can we do that, this kind of construction, for any given category? So you give me a category, so can we construct a simplicial set having a property like this? Which one? Kan complex, we will see. We will see. We will see in a minute. Okay. So let's first discuss this. Now, instead of, okay, in the first construction, you give me a topological space and I constructed this particular simplicial set having that property. Now let us start with a category. So given any category C, actually one can always define a very particular simplicial set, what we call nerve of a category, right? So one can define a simplicial set. So our notation is this, and let's call this one the nerve of a category. Okay. So let's see the definition. So therefore, you need to specify the n simplices, right? And here, the n simplices of that simplicial set. Okay, you know, this is just all composable maps having length n, right? So it's like you have maps like this in C. I mean, this is a composable maps in C, you know, having length n. Okay. And why this thing is important? Because by study the nerve of a category, you can actually understand the category itself. You know, the important remark: this nerve determines C, right? So in what sense? First of all, let's look at the objects. The objects of C, you can actually easily see that they correspond to the vertices, right? Vertices of n C. It means when n is 0, right? Because when n is 0, okay, so it means you just consider all possible x, because n is 0, x in C, but this is just objects of C. So therefore, vertices corresponds to, so they correspond to the objects of C itself. And as you may guess, if you look at morphisms, so they are like, edges, right? Edges in your simplicial set. Okay, let's observe this one. So morphisms, let's say you have a morphism like this from x0 to x1 in C, and this actually corresponds to just an edge, right? So something like this. So this is like x0. Let's say, I don't know, this is your phi, and this is your x1, and this is an element of nc0, nc0, and this one is just the element of nc1, right? One simplex, an edge.
This is direct.
What?
This is
Yeah, this is directed. Yeah.
earlier ones.
No, we always have a directed picture because remember we have an order always like this. Right? And if you apply this delta maps, it's like delta 0 phi is your x0, so your faces, right? And x1. Okay? And then you can do the same thing for the diagrams like this. So given any diagram like this, for instance, x0, x1, x2, and you have this composition, right, in your category. And this corresponds to, right, as you may guess, pictures like this. Let me just sketch the pictures. For instance, there is some sigma here. Let's say this is x0, x1, x2, and this is, let's say, G composition F, F and G. Okay, here this sigma is an element of NC2 and others, as you may guess, and you have the face maps and everything. Oh? So we have such a correspondence. Good. Actually, you can, so maybe you may sense why these kind of pictures are important, because existence of such a picture, for instance, this extension, kind of related to existence of a composition. Okay. So remember, last time we discussed in infinity categories, we have a problem with compositions, right? The composition is not well defined. Now somehow this kind of pictures, so as we shall see, kind of useful to, I don't know, specify an infinite category using that language. But let me just mention several other remarks. First of all, this simplicial set, this nerve, has a special property. So any simplicial map, from the ith horn to nc, okay, can be extended to a map, from yeah, we almost have that kind of picture, but we need to be a little bit careful, because this is true not for all I, only for what we call I don't know, interior horns. Okay, so extends uniquely to delta n. Okay, so as you just said, this is very important, because it basically tells you that, for instance, I don't know, let n equals 2. Okay, so when n equals 2, let's study what's happening. I mean, of course, we only have one possibility, because 0 I n. So only this diagram, right, can be fillable, let's say, x0, x1, x2, F, G, only this one is fillable, which corresponds to G composition F. Because if you remember the other possibilities, so for instance, this one, of course, this is a problem, right? So can we always extend these kind of maps? But there is a unique way of doing this in that situation by just using the composite, right? But here we have an issue if we have maps like this, or if we have maps like that, again we have a problem. So can we have this kind of map, right?
I'm now quite curious about how you actually took two morphisms, three morphisms in terms of nerve between. I guess it will be looking like we will have those interior.
Yeah. Exactly this. You want to do that thing for higher morphisms as well. So you want to somehow ensure the existence of such a map, such a composition, because this is only for when n equals 2. Just consider the higher horns, for instance, when n equals, I don't know, anything. But just consider the interior horns. But this actually motivates us to understand the relation between the existence of such a unique map and, let's say, this extension property of such a map. Okay, so there is a nice relation between these two. So this is very important motivation, but be careful. Here we have a nerve actually, right? So therefore, this nerve construction is kind of a motivation to give a more general definition. Okay, so this is just a starting point, and actually, why this is important example, the nerve construction. So just like in the previous part, our motivation was the construction of this special simplicial set. Now in the second part, our motivation is the construction of a nerve of a category. But we know that, so there is a important fact. Okay, the first maybe the fact is any category, right? It can be determined by its nerve, but actually we also have this nice relation. So given any simplicial set K, okay, simplicial set, you can always realize this simplicial set as a nerve of a small category, okay, for some small category C, okay. So for any simplicial set can be realized as a nerve of a small category, okay. Yeah. Yeah, it satisfies the property. So therefore, this is kind of our motivation. So therefore, this leads us to following definitions. So let's see. But of course, you may ask, okay, so if you look at carefully, we want uniqueness. Maybe you can drop this uniqueness. Okay, actually, for infinity categorical setup, as we shall see, why uniqueness, right? So you can drop this condition actually. This is actually what we are going to do. So therefore, this leads, I don't know, the following observations. First, the first observation, uniqueness issue, maybe we can drop. And the second thing is, this essentially tells us that some class of simplicial sets, it can be used as a model for infinite categories. Okay, so the sum class of simplicial sets can be used as a model for an infinity category. Okay, so let's see how. Sure.
I'm aware that the condition is needed for composition, but I cannot imagine anything.
Mm-hmm. Maybe one more. What you mean?
For number two, given a sufficient
Uh-huh.
we can see a number of categories. You said the above condition is necessary.
Just consider the foreign stuff.
Yeah, I mean just for horn.
Foreign doesn't.
Um, okay, so so therefore we have the following question. So the question is, so under what condition or conditions does this K, I don't know, behave like an infinite category or higher category? So under what condition does this K, I don't know, behave like a higher category? Okay, and this is, here is the condition. So our answer is answer is, let me call, I don't know, did I erase this? So answer is, we are going to use con condition, but not exactly. We drop the uniqueness. Okay, uniqueness dropped. Okay, so therefore we want, let's say, the extension property of the pictures like this. Sorry? Ah, yeah, you're right. So I just forgot which one. Yeah, you're also right. And also we only consider the interior horns. Or let me just say con condition. I mean, the new condition we will call weak con condition for interior horns only. Okay. So I mean, we will call it weak con condition. Okay, the new version without uniqueness, and we just require this condition only satisfy, you know, for interior horns. This is called the weak con condition. Okay, and therefore we only interested in the, let's say, extension property of pictures like this, and we only just want the existence of such map. Okay, so we have the following definition, and infinity category is a simplicial category, simplicial set K, for which, let's say, each simplicial map, you know, from the interior horns like this for any 0 I n, only interior horns, extends to this map. Okay, and the new condition is called the weak, let's say, weak con condition. Okay, so long story short, we just call an infinite category, or we just define an infinite category to be a weak con complex. Okay, so define an infinite category to be a weak con complex. Okay.
So we say the composition is the homomorphism between F and G, but what are two morphisms?
So two morphisms are just your insight, actually. What you glue inside your two simplices are your like two morphisms, and then you consider when n equals 3, which means that you are just attaching a 3 cell, you know, to your complex, and this turns out to be your 3 morphisms, and the story goes like this. Okay, and remember, only problem, I mean, the key problem for infinite categories, compositions are not well defined, always up to something. something. And now this kind of building blocks, let's say, allow us to encode such an information, but by using this extension property, but only for interior horns, because only for interior horns you have the information you are looking for, this composition, because these two things are, as you see, these are outer horns, right? This is when I equals, okay, which one? 2, right? 2, 2. This is 2, 0. These are outer horns, but they don't capture what we are looking for, right? Okay, so any other question so far? So when did we start? Kaçta başlamıştık ya? Do we have any time? I don't know. So we don't have that much time, but maybe so let me just tease you the next topic, and then maybe we should stop. So the next, I mean, actually we just finished discussing, you know, different but equivalent ways of specifying an infinity category. And now the next we will focus on the following object. So we just consider this category. Okay, and this is actually what we call the category of commutative differential graded K algebras. Okay, and they all so we have in non-positive degrees. Okay, in non-positive degrees. So let me just briefly discuss this category, and then next time we will see why this category is important. Okay, in the sense that we can actually use the elements of that category to build what we call derived affine schemes, and then derived schemes. Okay, maybe first thing I should mention here, this is a category carrying a model structure. Okay, so it has a model. This has a model structure. And remember, we discussed this before. If you have a model category, then by using the weak equivalences, you know, using this localization procedure, you can define the corresponding infinity category, right? So this was the easiest way of doing this. So therefore, this has a natural infinite categorical realization. So therefore, this model structure determines infinite category of CVGAs. Okay? Quasi-isomorphisms, you're right. So the weak equivalences, these weak equivalences are just quasi-isomorphisms. Okay? But actually, I don't know, so except for the proofs, we just treat this thing like an ordinary category. Okay? But just for some technicalities and proofs, we will see this infinite categorical nature. But for the next talk, actually, if you want, you can just consider this thing like a usual category. Actually, objects will be the same, so the only difference is this higher structural parts. So let me just briefly tell you what kind of objects you should expect to see. So the A, so you have a grading like this. Okay, non-positive degrees. So therefore, it's like you have a 0, a minus 1, a minus 2, and it goes like this. Okay, and here each AI is a K vector space. Okay, each AI is just a K vector space, and you have grading in non-positive degrees. Also, you have that exists a natural, you know, there exists k bilinear associative super commutative multiplication, right? Define on those things, which means that you can multiply two graded elements, right? So it's like you have. So I will explain. So it's something like this.
Is there a unit?
Yeah, you have a unit in A0, only in A0. Yeah. So you have this kind of product, of course, and the supercommutativity means it's like if you just change two elements like this, it may commute or anti-commute depending on their degrees. Okay, and this notation is degree. Okay, so you have a homogeneous degree, so each A. Okay, so therefore you have supercommutativity means when you change the places depending on your degree. So this is a k-vector space of degree I elements. Okay. Yeah, I mean, you have also a differential. You have a differential, and you have d squared equals 0. You know, you have a Leibniz rule and everything. And such objects we will usually use a notation AD or just A. Okay? If it's clear from the context, you have some D, and sometimes we use A or AD. Okay? So therefore, next time we will study the infinite category or just category of these things. Okay. By the way, these are just objects, and morphisms are like just chain maps. No, maybe I should mention over here, and then we should stop.
This interior allows the non-invertible one morphism.
Non-invertible one morphisms. Yeah, you have. Otherwise, yeah, because we only allow. I mean, for n equals n greater than 2, you have all morphisms are invertible. Only possibility that you have non-invertible morphisms are just one morphism. So okay, and let me quickly mention morphisms as well. So if you have a morphism like this, okay, so means you just have a chain map, right? So a chain map of complexes. It goes like this, and B0, B minus 1, B minus 2. You have maps like this.
No condition about multiplication.
No condition on what?
About multiplication. So you just said chain map. So no condition about
I mean, chain map and these diagrams commute, and other than that, we are not requiring any extra condition. Okay. I mean, of course, we are just imposing these. I mean, because there are some d's, so these squares must be commutative. But other than that, so these are like ordinary chain maps. Yeah, chain maps with commuting squares.
does that give you does it automatically preserve the bilinear multiplication? Just commuting diagram.
Well, let me think. So what do you mean? So you want to you want to preserve what?
So
You have
times there's a multiplication.
yeah. You have an associative k bilinear multiplication map.
So this chain map, as you define it, does it automatically preserve that as well for all k?
Yeah.
Ask the same question.
I see. Um, so no, we are just consider it like just the chain maps here. Maybe I should check. Yeah.
Weaker condition.
Okay, yeah.
Preserve
Yeah, this is too much a little bit.
preserve the multiplication is too much.
Yeah, this is too much. So here is the weaker condition. Okay. Yeah, I guess. So there are other things. So next time we will see the properties of this CDGA, category of CDGAs, and what kind of objects we can produce by using these things. And then we will define higher spaces. Okay, so maybe we should stop here.
Okay, any questions? Any further questions? I have two.
Mm-hmm.
Is there a natural example of this CDG?
Yes, I have. Just consider like a graded polynomial algebra, or maybe one example. I don't know. Just start with A0, let's say, to be just this usual polynomial ring. Okay, just introduce new variables, maybe A minus 1. I don't know. Actually, I was planning to give this example, but for instance, introduce a new variable y. Okay. Now this is a module over this, and plus, I don't know, maybe something like this. You can introduce another variable like this, the module generated by this. Okay. So this is maybe your a minus 1, and a minus 2 is like you can directly use the module generated by these elements over that. Okay. And let's say the rest is just 0. Okay. But this could happen. So the natural things or the natural examples are like graded polynomial algebras. And you are just adjoining new variable in other degree. So you're starting with some K algebra, for instance. So you are just adjoining new variable in other degree, and you just consider the corresponding module. And there is a way of constructing such CDGAs, but this is a very natural example. So the graded polynomial algebra, okay, in all grades, in negative degrees. Okay?
You just construct Kx with x being b minus 1.
Yeah.
That would also be
Yeah. So here x is like degree 0, y is like degree minus 1 variables. Okay. When you multiply, this is degree 2, but this is just degree 0, so this is still degree 2, minus 2. Okay. But this is one way, so one example. Of course, what is the differential here? So this is just a graded algebra part. We also introduce a differential. I don't know, maybe next time I can show it, but it's not that much hard. Okay.
You said we use the model structure only to prove. I don't know if this is a hard question.
Yeah.
What kind of freedom or power that?
So it's like in infinite categorical setup. So you don't have, I don't know, so you will have diagrams like this, but you have higher diagrams up to something. So you don't have strict commutativity in general. It's always up to homotopy. Okay? So therefore, in proofs, you have to use this homotopical perspective actually. But since we are not going to prove anything, I mean, if you consider CDGA as a category, or if you consider so they generally use this boldface, infinite categorical version. Actually, they have exactly the same objects. So no problem here. But now you have higher morphisms and everything up to homotopy, and the composition is not well defined. So you have higher coherence conditions to satisfy. So therefore, things getting messy. Okay? So therefore, when you prove things, therefore you need to consider it a little bit carefully. because diagrams will not commute strictly. But for us, since we are not going to prove anything, we don't need this technical details. But in proofs, I mean, if you want to prove something in this language, you need to be careful. You need to deal with this higher coherence conditions. But we are not going to do that. So for us, it's really understand behind the scenes there is this infinite categorical discussion. But for simplicity, if you want, you can just consider objects, morphisms in a usual categorical sense. It will be enough for us.
N morphisms are degree minus n chains.
Here,
Yes.
yeah.
You're saying higher morphisms. Are higher morphisms like n morphisms are degree minus n morphism chain? Or
I think so. It's like so. It's like I don't know how should we see it. So you just consider this diagram and one more diagram. So it's like you have higher chain maps. So between these two things, and you want to commute, you want to ask commutativity of higher diagrams. So it's like you, instead of a picture like this, you consider a diagrams like that. Okay. So in each corner you have these, and therefore you ask commutativity of all of these things. So therefore still you have chain maps but higher coherence conditions. So something like this if you want. I don't know. This is maybe the easiest way of seeing this. Okay. So it could be another map joining these two. For instance, this part, this face of this cube, and the old map, and you want these things up to homotopy between these two. So therefore, you ask a higher commutativity diagram like this. So still you have chain maps, but yeah.
so somehow it's giving a degree one.
Yeah,
It's a
the chain
homotopy.
homotopy. Yeah.
Degree minus one. And then
Yeah.
degree minus two.
Yeah, you're right. Yeah, I think so. You're right.
I guess from this commutative diagram, the only information you'll get is the degree n of minus n.
Mm-hmm, mm-hmm. Okay.
I think it would be cool.
Yeah, I think so. Yeah.
How about the cochain complex of singular simplicial set of it? That would be an example of it. With the cup product between cochains as the algebraic structure, the multiplication.
I don't know. Could be. Could be. Could be. I don't know.
Yes.
I see. I mean, because I mean, the reason why this is more natural for me, because later these A's, I mean, if you are, in usual algebraic geometry, everything is about understanding spec A, right? And A is like some commutative algebra. And for instance, you may have some polynomial ring divided, you may have some quotient, you may discuss a scheme, right? So therefore, the natural thing to expect over here, some kind of polynomial or some quotient of it. But this is the algebraic geometry part. But here, instead of this non-graded objects, just the commutative K-algebra, which is actually here, only this part. So if you just forget everything on the left-hand side, if you just consider this part, you are doing algebraic geometry. Okay, so this is your ring of function, actually, right? So therefore, you should expect to see some kind of graded polynomial structure. I don't know, at least for me as a natural example, you should expect to see some graded polynomial algebra. But depending on your motivation, yeah, maybe you may have other examples.
The cup product on the cohomology of finite groups was indexed by positive numbers. It has this same linear association.
Yeah, cup product thing. Yeah, you're right.
But the indexing is different. So
Yeah, I mean, this is
Cup product of homology.
Cup product of cochains, you can take cup product of cochains.
yeah.
But the direction goes in the wrong. Yeah. So I think you're thinking A0, A1 for the first degree.
This could also happen.
But the cochain
Yeah.
would go from 0 to 1.
Yeah.
How do you?
It's just, I mean, just consider the, well, here A minus 1 to A0.
Yeah.
Yeah, maybe here. Yeah, I don't know. Yeah. Yeah. Okay.
Okay. Let's take it. Yeah.
So we continue next week.
Not next week, the other week, the other one, 2 weeks.